Darkness is the absence of light, but if you look carefully enough, you might just see even darkness. Our astrophysicists have been looking into deep space since 1802. They found out that it's not so empty after all. Using the largest optical telescope in Northern Europe, researchers at Tartu Observatory are conducting detailed studies of galaxy formation and superclusters in the universe, where dark matter dominates. Our scientists are developing cutting-edge space technology, testing and calibrating it for rough conditions in space and on Earth. The advanced technology allows humans to observe Earth from space and therefore understand its resources. Since 2013, we really belong amongst the stars. Close international collaboration and a motivated team allows reaching new heights. We are constantly filling the space between us and the universe with knowledge. Time to observe, united by space.
Dear ladies and gentlemen, dear guests, dear colleagues, I am very happy to welcome you here in Tartu Observatory. This is a very important event for us because the conference about space technology is held in Tartu Observatory time, and we have so much to celebrate with this conference. First, it is the first conference in Tartu Observatory in this new building, where also start of first Estonian satellite was monitored about 1.5 years ago. Also, just with this week, we celebrate the 50 years of Tartu Observatory in Tõravere. Actually, the Estonian space research is 200 years old, but old observatory is in town and it is museum now. So, all you who are here, young people, experienced people working in developing small satellites, nanosatellites, I see you as leaders for the space activities in the future. And it is very important for us, for Estonia, that you came here and you share with us our interest, our competencies, our skills to develop this new modern technology. So during the conference, we give words for experienced researchers who can visualize how the future will look like, but also for the young starting students who can already demonstrate what are their wishes, capacities to realize this future. I am leading the first session, and I think the first session we will learn about Estonian first light, of course, but also experiences with Estonian first satellite. And I guess that Pekka Janhunen we can call our guru in this field, because his support for our activities has been really, it is difficult to say how big, because I guess it was very, very important to meet Pekka first 7 years ago, and his ideas to develop technology in Estonia has helped us a lot. But before we start with first session, I ask here to come Jan Raks and talk how was yesterday's event, how student behaved, and who was winner of the competition.
Good morning, everybody, and welcome back to this wonderful conference and workshop. And I have to announce now the winners. The jury had very tough work to do, and we had long, very interesting discussions about all these very thrilling and fascinating ideas. You can bet we found a lot of also problems with your ideas, But however, we also found the best of the teams actually in several categories. So, the best science fiction prize goes to Moondrop Mission. Applause. The best presentation award goes to Test Tube Mission. The best requirement derivation and instrument selection prize goes to the Firesat mission. And the best and the most original science case prize goes to the Kara mission. Additionally, the Kara mission will get also the special nomination on utilizing best the CubeSat philosophy and form factor. Thank you very much.
So I hope you will get some rice, at least lunch later. But now it is time to go to our working session. So I ask here Pekka Janhunen. Pekka is from Finnish Meteorological Institute and is also working as guest professor in Tartu University.
Okay, thank you very much, Rami, for this kind introduction. Let me set the laser and so on. Okay, so good morning, everybody. So I will talk about space exploration with electric solar and say this is the title that Mart gave to me today, or for today's presentation. Here is a list of contributors to this presentation. There are quite many of them, as you know, because most of them are from this ESA FP7 project, who develop different component technologies of the ESA. The contents of this presentation is the following. So I kind of describe the positive and negative polarity Coulomb-Drake effects or phenomena. Then I describe especially the positive polarity case, which is the ESA, interplanetary ESA. Then I describe the negative polarity case, which is the ionospheric plasma break. And then ST1R1 CubeSat mission, something about them. And then applications. And this applications part is rather long in this presentation, so I will go rather quickly over these starting slides. So, positive polarity Coulomb-Drake. Here is a kind of a simulation about it. So here is the tether, a charged tether, positively charged tether, put in solar wind plasma stream in this case. And this is particle in cell simulation, so it means that one follows the trajectories of ions and electrons in the self-consistent electric field of the ions and electrons. So it's electrostatic plasma simulation. And then physically what happens is that there is a deflection of ions, so the electric field of the tether repels the ions. So when ion comes here along a straight or more or less straight trajectory, it gets pushed sideways or deflected, and then because of that it loses like x-directional momentum. So x is in the direction of the original flow. So the momentum in the original flow direction gets reduced and it gets turned to y-directed vertical momentum partly. And this kind of causes permanent heat. I mean, in the fluid picture, this causes permanent heating of the flow, which was originally like almost monoenergetic beam. It becomes more warm beam, which has also perpendicular velocities. And this is the energy source. I mean, this conversion this creation of entropy from the physics point of view is the kind of the energy source of this propulsion system. So this x-directed momentum, which is lost by the particles, it gets transferred to the tether. And then electrons are doing more or less the same thing. So electrons want to go where ions are going, more or less. So there is an electron wake, vacuum behind the tether, and also ion vacuum, and so on. But from the propulsion point of view, only the ions are important, because ions are about 2,000 times more massive than the electrons. So where the electrons are going, it does not really matter so much in this case. There are nowadays also some laboratory measurements of this electric shell phenomenon. So CQR et al. Last year, it's a group working in France and Spain, ONERA in France. They made some measurements not for the purpose of simulating the E-sail, but for the purpose of trying to understand the current collection of a charged tether for the purpose of the electrodynamic tether propulsion. But the measurements they made are kind of applicable to the E-sail case, because what they made, they scanned a Langmuir probe, which is basically a measurement device for plasma density, local plasma density. They scanned it in the two-dimensional plane around a charged tether, which is sitting here, and they created a map of the electron density. So here is the wave. It is similar as in the previous simulation, this blue thing. The only difference is now the flow is arriving from the right-hand side. And this is, this is the result for a certain voltage, 100 volts, and this is for a higher voltage, 400 volts. And when one looks at the plasma parameters and ion masses and all the stuff what they have in this experiment, and if one applies kind of our semi-empirical theory, which is based on our simulations, then one gets very good agreement between this sheet thickness of the laboratory experiment and our theory. So kind of this supports the idea that the E-sail force might even be maximal in some sense. So in the sense that there seems to be, in this laboratory experiment there is no indication of extra shielding by trapped electrons, which could reduce, in principle, reduce the thrust of the E-sail. So this is very good news for the E-sail. So the laboratory measurements are consistent with the idea that there are no trapped electrons, in which case the E-sail effect has the kind of the maximal value, which can be also more easily analyzed from the theory point of view by just assuming that trapped electrons are absent. Here is a picture of the negative polarity Coulomb drag. So, the same but with negative polarity. So then the physics is different. So then the electrons, these are electrons, they are strongly repelled by this negatively charged tether. So there are absolutely no electrons in this blue region. But on the other hand, ions are attracted by the tether. So ions are making close-by passes near the tether, but nevertheless they are deflected from their original direction. So the tether's electric field is scattering ions, a little bit in the same way as if a comet is arriving from the distant solar system and makes a close pass of the sun. So then what happens is that the sun deflects the comet to another direction. So the same thing happens here also. And the net result is a transfer of momentum again from the flow to the tether. This simulation is made for low Earth orbit parameters, not for the solar wind as the previous one. In principle, one would use both negative and positive polarity anywhere, but for certain technical reasons, it seems to be better to use the positive polarity in the solar wind and the negative polarity in low Earth orbit conditions. We have some thrust and power consumption estimates for the electric sail and for the plasma brake. So, one noteworthy thing about the thrust in the E-sail case is that the thrust scales as 1 over distance from the sun. So it's not 1 over distance squared, but it's 1 over distance, which means that our thrust decays more slowly than the thrust of the photonic cell, for example, or also the thrust of the solar electric propulsion, because even in solar electric propulsion, the power produced by the solar panels decays as 1 over r squared, and so the power available for propulsion decays in that way, and in that sense also in that propulsion system, the thrust decays. Okay. E-cell construction, so I think you have seen these figures before, most of you. So the baseline idea for this interplanetary E-cell is that we have a spinning system where the tethers are stretched, and then the system is dynamically stabilized by connecting together the tips of the main tethers by something that we call the auxiliary tethers. And then if one does that, then one has to have these remote units at the tips, which contain the reel of the auxiliary tethers, and the remote units also must contain some spin-up propulsion and perhaps spin control. So the spin-up propulsion means that one has to create the initial angular momentum somehow when deploying this tether system. Okay, then we have this EU project which completed in November last year. It fulfilled all its goals basically. So we produced 1 kilometer tether sample at the University of Helsinki. We demonstrated unreeling after vibration test. So we vibrated the reel at the tether and then tested if the tether still comes out, and it does indeed come out. And then we tested the tether in vacuum and under also high voltage conditions to for example, to measure the effect of the electron bombardment of the tether. This was done in Finland, in University of Jyväskylä. And then mainly the Swedes, but also Estonians and other Italians and Germans contributed. They built this remote unit prototype. And then at FMI we made this flight simulator. It's not very well visible, but it's in a software which simulates the dynamical flight of the E-cell in the solar wind. Here's the tether factory, picture of the tether factory. Another picture of the tether factory and this 1 kilometer reel. Here's one wire bond in the tether, a scanning electron microscope picture of that. And then here is the tether itself. So it's multi-line tether where 4 wires are connected at a few centimeter distance to each other. And these connections are made by ultrasonic bonding. The reason for this a bit complicated structure is that is micrometeoroid tolerance. So if there were no micrometeoroids in space, then this tether would simply be just a single wire, which is 20 kilometers long. It would be very simple to make. You could just bind a wire and deploy it without complications. But since there are micrometeoroids in space, one has to make it this redundant structure so that micrometeoroids can break these wires here and there without breaking the whole structure. Then this is the dynamical simulation. Okay, I will not say more about it. Then plasma break. So this is the ionospheric application with negative tether. So there the idea is to use the spacecraft conducting body as the balancing electrode. So one biases the tether negative in this case. And then, I mean that one forces a potential difference between the spacecraft body and the tether in such a way that the tether is more negative than the spacecraft body. And then what happens is that the spacecraft body tries to go positive with respect to plasma, but since there are lots of plasma electrons in the ionosphere, this electron flux will kind of prohibit it from going much beyond zero potential. So in fact it will settle to some very small positive potential, maybe fraction of a volt or something like that, fraction of the electron temperature. And this electron temperature is very small in the ionosphere, 0.1 electron volts. So in practice this spacecraft body will be very close to zero from the tether's point of view, and the tether then goes 500 volts negative or 1 kilovolt negative or whatever the voltage source is forcing. The reason for using negative polarity in this case is that, well, the main reason is that it uses less power than the positive one, because ion, if you gather ion current from the plasma, it's much, the current is much less than electron current, because the mobility of ions is much less than the mobility of electrons. Okay, S-cube, well, you know all about it, so I don't, and also Mark will tell in the next presentation. Then Arto mission, planned launch next year. Similar experiment than in S-cube, but longer tether and renewed hardware, but otherwise in principle functionally similar. Okay, then I will discuss the ESA applications. So this will be the longest part of this presentation. So, especially, ESA applications, also the interplanetary applications. So, ESA would make basically any interplanetary mission faster, cheaper, and better in some sense. Almost any means that not quite all of them, but a large subset. And this genericity stems from the fact that the ESA only needs the solar wind to work. Of course, there is also a limitation here, so that because the region where satellites are orbiting does not have solar wind, so it means that one cannot apply the ESA for raising satellite orbits, for example. So this is unfortunate, but it is a fact that with which we have to live with. So satellites still need traditional propulsion, but once you are out of Earth's magnetosphere, then the ESA can be used. Or then the ESA principle is applicable, let us say so. So we will look into giant planet missions, then non-Keplerian orbits, sample return missions, and also so-called data clippers, which return data instead of physical samples. And then asteroids, last but not least, asteroids, because the ESA can address all aspects of asteroids, studying them, touring them, and then Earth protection, planetary protection, and then in the future perhaps also mining, asteroid mining. Well, anyway, we start with giant planet entry and flyby. So this is like rather straightforward application from the ESA point of view. So one just uses the ESA as a one-way booster for the outer solar system. So instead of using, the present outer planet missions are using Venus, Earth, complicated gravity flyby maneuvers and chemical propulsion. They work, but there are two drawbacks. So one is long travel time. The other drawback is the dependency on launch windows. So one has to launch at a certain date in order to catch these planetary assist maneuvers. With ESA, you don't have this limitation. So one can launch almost at any time. Or, there are still some more preferred times than others, but in principle one could launch almost at any time. And then what one does in the outer solar system is then another question. So with another question which is not related to the ESA. So for example, it could be atmospheric entry probe. It could be flyby, for example, of some smaller outer solar system objects, such as one of the moons of Neptune, for example, or one of the so-called Centaur objects, or Kuiper belt objects. There are lots of objects in the outer solar system about which very little is known, because they are just dots. They are just dots in the telescope. Perhaps some spectra are known, but no imaging. So if one wants to take any images of them, then of course one has to make a flyby or a close approach. And then orbit capture by small chemical burn. So this orbit capture is important thing. So the ESA, I mean for the outer solar system, the ESA only enables one-way travel. So it only can boost, it can throw the payload at a relatively high speed into the outer solar system, but it cannot stop the payload in the outer solar system, or at least it's not relevant. It's not a good idea to do so because it would take a long time. But then, in case of giant planets, there is a so-called Obert effect, which is nothing mysterious. It just stems from the orbital dynamics. It's a consequence of the conservation laws of inertia and angular momentum. But it basically says that if one makes an impulsive chemical burn near the massive object, then the effect of this burn is like magnified. So it means that, for example, if one approaches Jupiter at relatively high speed, let's say 15 kilometers per second, I mean speed which is originally produced by the ESA, and then the probe is flying outward in the solar system and then entering Jupiter's gravity field 15 kilometers per second, for example. Then Jupiter's gravity field will accelerate even more, and if it flies very close to the surface of Jupiter, its speed becomes more than 60 kilometers per second because of the very high gravity field of Jupiter. And then if one makes a braking burn at the point where the velocity is the highest, so if one reduces the speed from, let's say, 64 to 63 kilometers per second, then one finds that when the spacecraft again kind of goes away from Jupiter, it cannot anymore escape the gravity field of Jupiter, but it has entered into elliptical orbit around the planet. So a very small, relatively small chemical burn is enough to capture the probe to orbit around Jupiter, even though the incoming speed is much higher. I mean 15 kilometers per second, for example, which is much higher than any chemical propulsion could do. So, but this works only with massive planets. So it works extremely well with Jupiter, it works relatively well with Saturn, it works less well with Uranus and Neptune, but still it works there. So, but anyway, so this is a kind of limitation that must be kept in mind. So if one wants to, I mean, the ESA does not enable, for example, an orbiter around Pluto. I mean, this is impossible because Pluto is too lightweight object. You can't break with any reasonable chemical burn. So this is something which is not possible to do with the ESA or any other known propulsion system for that matter. Anyway, in this table there are some flight paths to these giant planets. Of course, especially if we are considering atmospheric entry, then this question of stopping is not a problem because we simply ran through basically collide with the planet and then the heat shield takes care of the braking. And I mean then in that case these are the flight paths that we could receive. And scientifically these atmospheric entries would be very well motivated because thus far only Jupiter's atmosphere is known accurately. I mean the chemical and isotope composition of only Jupiter's atmosphere is known. Saturn, Uranus and Neptune are unknown, basically unknown. And it would be very important to know also these atmospheres because it constrains the evolution theories of the solar system. So after measuring those atmospheres, we would know how the solar system actually formed. For example, whether the giant planets actually changed position in some early phase of the solar system. I mean, such theories exist, but there is no definitive proof. So the early history of the solar system was likely quite dramatic, but we don't know for sure. But this would be a way of probing it. Okay, then non-Keplerian orbit. So instead of going somewhere far, one could also use the ESA for staying where you are, but in an orbit which is kind of unnatural. So some orbit which requires constant thrust in order to maintain it. So one would apply it to Earth observation, remote sensing, and other solar system science. So, for example, off-Lagrange point solar wind monitoring, space weather forecasting with longer than 1 hour warning time. It would be possible with ESA. In fact, it would be possible even with a 3-unit CubeSat probably. It would be possible almost with the same, essentially the similar hardware, similar platform, what we know as SQ3 and SQ2. Because actually the ESA can produce it can produce data of the solar winds without any ion instrument. So it can produce the measurement of the solar wind density just by measuring the tether current. I mean, if one knows the voltage of the tether, then by just measuring the tether current, one gets to know the solar wind density. And then, if knowing the density and the voltage, then measuring the thrust, one can get the measurement of the solar wind speed. Perhaps even velocity, so perhaps even the directional information, but at least a rough estimate of the speed. And then the only thing one needs to measure the space weather, the solar wind, is to add a magnetometer. A suitable magnetometer exists. It has flown already. Its name is Magic, made by Imperial College. It has flown in cinema CubeSat, about 200 gram magnetometer with a 1 meter boom. So it would enable monitoring of the solar wind, all the important parameters of the solar wind. So magnetic field, plasma density, plasma velocity, with a CubeSat platform on the sunward side of the Lagrange point. So with 1 kilometer tether and with 1 kilometer tether and 10 kilovolt voltage, one would increase the warning time by 13%, which is about 8 minutes with respect to the standard 1 hour warning time. Okay, so that was it. And then also from the Lagrange point, one would, if one instead of having the plasma instruments, if one mounts a small telescope, where one could watch Earth approaching near-Earth objects and so-called pseudomoons. Pseudomoons are small asteroids or rocks which spend some time, they kind of arrive to the Earth-Moon system and they spend some time orbiting there and then they are usually ejected out. And they usually enter kind of through the Lagrange point. So they, in order to stay in the Earth-Moon system, they must enter somewhere near the Lagrange point. And then to detect them, the telescope should be on the sunward side of the Lagrange point so that one sees these objects in good visibility conditions so that the sunlight is in a favorable direction with respect to the observational point. And then the interest of these pseudomoons is that once such a pseudomoon is found, then ground-based telescopes could be mobilized to hunt for it and make accurate observations. But the bottleneck is that we don't find these pseudomoons. We know that, statistically, we know that they come to our system, but every now and then they are not extremely rare, but it's hard to find them, so that is the bottleneck. And you can't find them from Earth because from Earth you would be watching almost towards the sun if you want to watch the Lagrange point. So you can't see anything in that direction. Okay, so perhaps I will not discuss those others in detail. Okay, and then about sample return and data clicker. So because the ESA kind of is free propulsion, so if one can use the ESA for going somewhere, in principle one can use the same ESA for coming back, and the return trip has no additional cost because no propellant is consumed. So one would return physical samples, but returning these physical samples is of course very highly motivated from the science point of view, but it's also quite rather expensive. I mean, regardless of the free return, returning samples is quite inherently expensive because one needs to deliver, somehow return them to Earth's surface, so one needs this return capsule. Well, it's not known technology, but it's not CubeSat thing. So we are talking about rather big missions. Then And also these samples, when they return to Earth, one has to curate them and handle them properly and make sure that they are not dangerous to Earth and so on. But in a lower cost way, one would, instead of physical samples, one would return large amounts of data with the ESA on flash memory chips. So flash memory chips are very dense nowadays, and they can be shielded against radiation enough to be able to contain terabytes of data. And this terabytes of data is so large amount that you can probably never be able to radio it down from the distant solar system. And in that sense, it's kind of enabling technology for returning large volumes of data from distant targets in the solar system. For example, high-resolution images, even high-resolution video of landings, whatever landing sequence of an asteroid. For example, we now have the Rosetta mission, has returned very beautiful pictures, but imagine if you would get high-definition video out of all sequences, all the landing sequences. I mean, you would get video which lasts for weeks or months continuously. Every aspect of the mission would be documented, plus tons of other science data. And it would be possible if Rosetta would carry a small ESA probe, which it would detach after the mission. It would return to Earth, not necessarily to Earth physically, but it would return to Earth's vicinity, and then one would download the data from the ESA probe efficiently using radio, but using fast link because it's close distance to Earth. So it would be low-cost way of boosting the science of any mission of this time. So I mean, people are not kind of used to think about it, but because they are used to. I mean, those people who are designing these missions, they are used to live with very limited telemetry budgets. Everything in the mission is designed with a very limited telemetry in mind, and there are always these hard telemetry negotiations with different instrument groups and so on. But this would be potentially a way to get around that limitation, to have so much data that you almost don't have to care in the best case. Of course, you would get the data after some years of delay, so you would still do the vision in real time with radio communication. So this high-resolution data would only arrive after the main mission, after some years, but it would still be valuable, very valuable from the scientific point of view. Then I go to asteroids. So multi-asteroid touring mission. So the ESA would enable touring the asteroid belt because it doesn't consume propellant, and so it can produce very large delta V total impulse, in principle unlimited total impulse. So one would visit many asteroids, near Earth objects, main belt, Jupiter, Trojan, any. Here are some formulas. So I mean, that how often one could make an asteroid flyby with this kind of system. This is very, very rough formula based on rough assumptions. Assumption of, I mean, ignoring all the orbital dynamics, just considering the asteroid belt as an asteroid gas with some like temperature, which is the velocity spread of the asteroids, and some density. So density of asteroids is n. The typical speed is v, and then a is the acceleration that the ESA can produce. So, but what is noteworthy of these formulas is that these exponents are rather small. So it means that this delta t, I mean, how often a flyby can be made is not very sensitive, for example, to the asteroid density. I mean, the density, that how many asteroids you have in a cubic astronomical unit, for example. And I mean, of course, asteroid density is, well, it is a constant. It is what it is. But I mean, but in practice, in this case, it means that how small asteroids we are looking. So if we are interested in very small asteroids, then effectively the asteroid density n is higher, because there are many more smaller asteroids than big asteroids. And then a similar formula for rendezvous. So rendezvous is more rare. I mean, rendezvous means that you not only make a flyby, but you also arrange the same speeds velocity, so that you are actually you can fly besides the object for an extended time. So in that case also we get this kind of formula. Again, it's rather easy, the result is rather insensitive to the asteroid density in particular. Then Earth protection. So an asteroid direct deflection would in principle be possible by the ESA. So for example, 1 Newton thrust produced by the ESA, it could move 150-meter asteroid out of Earth's path in a 7-year period. Out of Earth's path means that, so if a collision is kind of predicted with Earth and this asteroid, then by moving this asteroid by a distance sideways, which is more than 1 Earth radius, then one can avoid the collision. I mean, thinking of the problem from the coordinate system of the asteroid, so you are sitting on the asteroid, which is steady in its own coordinate system, and then the Earth comes flying, and then you just have to step aside so that the Earth can push by and not collide. Anyway, so this is a bit naive way to calculate it, because there are so-called gravitational keyholes, so I don't go into details, but it means that basically that the situation might be much better in many cases. Better in the sense that even smaller delta V would be enough to take an even bigger asteroid. The attachment is a technical challenge, of course. It's for any propulsion system, for the ESA in particular. I will not go into details about that. But then, I mean, regardless of, even if the attachment works, there is always the question that what if we don't have 7 years of warning time? What if we don't have almost any warning time? So then the only way is to make an impulsive, a fast collision with this threatening object, and hope that this collision will deflect this object from its course, so that this collision is avoided. So with the ESA, one could set up a retrograde, what we call a retrograde ESA planetary defense system. So one would put a set of masses into retrograde orbits around the Sun. And the retrograde orbit means that one can get very high delta, very high relative speed when this retrograde object collides with an asteroid, and therefore the deflection power of even a small mass can be magnified, because the impact energy is half mv squared, and now v is 60 kilometers per second. So one could reach 1 kiloton of explosive power from this kind of collision with a few tons of mass. And this is, if one is worried about such system, from the safety point of view, there is no reason to worry, because these masses would be made mostly out of liquids, for example water or any other liquid, so that this kind of mass or spacecraft filled with liquid, it simply vaporizes if it collides with Earth accidentally. So it can be designed for demise, as the orbital debris people are saying, in the unlikely event of accidental collision with Earth. Okay, and then last but not least, asteroid mining. So asteroid mining could enable qualitatively different space activity, because it could enable large space assets with asymptotically low price per kilogram. So here's a kind of instructive picture, so that one would have some asteroid, and this is taken from the website of one of these companies, which came online last year. So take an asteroid, and then you have some device, for example 3D printer here, which extracts, for example, iron and nickel metal from the asteroid, and then prints a space station using the asteroid material. And the space station, the mass is not limited by anything basically. So it could be 1,000 times larger than the mass of the printer, or whatever times larger. So this is kind of a wide idea which is not yet reality, but if it one day becomes reality, then space will certainly change. So here are my conclusions. So yeah, so you can read my conclusions, and meanwhile I'm happy to answer your questions. So thank you.
Do you think that could you slow down a spacecraft using the e-sail, for example, in Jupiter's ionosphere?
So you mean this in effect, even by using e-sail?
Yes.
So using plasma braking basically. Yes, why not? But only gradually. So are you referring to the case that we would first enter into elliptical orbit and then we would lower the apogee of the orbit by this method slowly, for example, or
Maybe you are going to pass Jupiter really fast, and instead of using chemical propulsion to stay there.
Yeah, no, you can't, because you can't produce enough. I mean, you can't produce the delta V rapidly enough with the e-sail method. So, yeah, no, you can only do it gradually.
Pekka, would you also say what is the time schedule for these experiments? After 10 years, 20 years, century?
With experiments.
But you
Whatever.
choose the closest one.
It all depends on funding. So I mean, we could. I mean, there is no reason why it would take more than 10 years to implement almost any of these. I mean, there is no technical reason why it should take more than 10 years. But of course, having said that, we don't know it, so there might be unknowns. So there might be problems that we are not aware of yet. But at least if I consider the issues that are currently open, there is no reason why implementing most of these ideas would take more than 10 years, given enough resources to do them.
I don't think I need a microphone. If you go to the next page, well, maybe next after that, you have this masses and so on.
This,
We talk a lot here about CubeSats, and you can notice that the smaller the mass of the payload, the faster you get to Jupiter. So
yes.
if you have a CubeSat or something, how long will it take? Can you comment on this?
Yeah, I guess it could be faster than those, but then the question is that what happens? I mean, what do you do with that speed? So then, I mean, if you increase the speed much beyond these, I mean, if you shorten the travel time much beyond these values, then if you are doing an atmospheric entry, then the entry speed starts to become problematic. And then, of course, you can't communicate from CubeSat from Jupiter distance to Earth, at least. I don't know how to do it.
Another question, can you steer it? Like, how do you hit Jupiter? It's still...
Yeah, you can steer it, yes. You can control the direction of the thrust by... I mean, you can tilt the sail with respect to the solar wind, so you can steer it, yes. So that is not it's almost as navigable as any other propulsion system, so I would say. So even ion engines are not completely navigable. I mean, even they are. I mean, the thrust direction is not completely known. I mean, you just apply the thrust and then you see what comes out and then you have to correct. So and the same applies to the e-sail.
Reconfiguring or sail is...
I mean, you don't you just tilt the you incline the spin plane by using differential modulation of the tethers. So this maneuver takes maybe maybe 10 hours of that order of magnitude.
That's the scale.
Yeah, that's the scale. Yeah.
A follow-up question or comment is that so CubeSat to Jupiter, we have to take into account that the propulsion system itself weighs the effective enhancement.
Yes. So these examples were calculated with 1 Newton e-sail with the assumption that it weighs 100 kilograms, I think, in this case. So haven't calculated. I mean, what happens if we go below this 500? So it would be certainly faster, but how much faster that I don't know.
So, but thank you, Pekka, and I see this discussion would continue during the day and tomorrow, and thank you, Pekka, really much. Now it's time to hear how S-Cube mission has proceeded, and Mart Noorma from Tartu University and also head of the Tartu Observatory Space Technology Department gives this overview.
Good morning, everybody. I'm Mart Noorma, as explained earlier, and I'm not presenting here alone, but we are presenting with all S-Cube team, and especially with the people who are around here in the hall. So the purpose of this presentation is to give the status update. Where are we standing now? 504 days after the launch of S-Cube-1 to the low Earth orbit. So, as most of us were taught yesterday by Jan Brax, when we start with a mission, then we need to very clearly define the mission objectives, and then we derive requirements from there, and then we develop the spacecraft. So let's come back to the mission objectives. And just a reminder, in case of S-Cube-1, our most important scientific objective was to test the deployment of a 10-meter E-cell tether produced by Helsinki University, and if successful in the tether deployment, then also measure the real force acting on the tether in interaction with atmospheric plasma. But equally important for the Estonian student satellite program and all Estonia was also the educational objective of the first Estonian satellite. And in the most general way to define the objective is that it is to support student learning at Estonian universities. And already shortly into the mission, when it started in 2008, this is a project, we expanded it beyond Estonia with wide international cooperation, and we hope that our partners also have benefited from some educational benefits. And also for Estonia, it's very important to promote subjects in science, technology, engineering, mathematics, because according to, let's say, all strategy documents in Estonia, the future of, or future happiness of people in Estonia depends on economic growth of the country, and the motor of the growth is seen as technology or knowledge-based economy, where engineers and natural science has a very important role. And it doesn't mean that everybody who graduates from high school has to become a scientist, but it means that people graduating from high school should graduate with as good knowledge and skills in science, technology, engineering, mathematics as possible. So they would make the correct career choices and would be beneficial for the society. And last but not least is a scientific objective which we really couldn't define in the beginning of the mission. So also what we have seen in S-1 is that sometimes in these space projects they work like student thesis writing or any research project. You start with your research, you define the objective of this research, you start, and then you see something else that works, or you discover, and then you redefine your objectives, and you turn into some other direction. So in case of SQ1, one thing what we saw from the very beginning was enormous interest from the Estonian society and media towards our space mission. So while in the earlier statements we said yes, we'll take one image of Estonia, which serves outreach purposes, then on the way we have seen that everything related to our ambitions in the field of space technology really motivate people. And now I continue with just a brief overview of where we are now in fulfilling these objectives. But just as a starter, let's look at this mission animation that summarizes the activities of our satellites in space. And now lessons learned from outreach point of view, of course, are, well, kind of self-evident, but good animations in explaining what you are doing in science are, let's say, not equally important as your science, but not much less important. Because as researchers, and especially in the SQ1 team, we have put a lot of effort on all team participants, all students, to understand as early as possible that we are on the payroll of Estonian and European taxpayers. We have to give them something back. And giving them something back is not so much scientific articles like this special issue on SQ1 technology. And even not like special issues on in popular science magazines on ESAIL and SQ1 technologies. But most importantly, it's about some things that people can be proud of. They can discuss with others, and they can say that yes, Estonia is a really good place to live, because some great things happen here all the time. For example, like at the end of the animation, the desert deployment. And some numbers that I collected here, which are not so much meant for very intelligent scientific community that we have in this hall today, but the numbers that we can proudly present to our employers, the Estonian and European taxpayers, to make them understand, to help them to understand what's going on, what this does it mean, the space mission. And 500 days already seems quite a lot for a spacecraft to operate in space, but for ordinary people, yeah, it's just a little bit more than 1 year, and they can't really see the very difficult work behind. We all remember from Jan's presentation yesterday that also mission operation can be almost as expensive as development of the mission itself. So here everybody can look at Erikulu, our spacecraft commander, standing there at the door. So this is a moment to give a big hand to Erik for his excellent work, because he's the person behind these 4,000 communication sessions successfully completed. During that time, ESCUBE has passed nice little journey of 328 million kilometers, which is already quite an achievement. I'm sure this is definitely, that might be a record for anything built in Estonia. I know, actually our instruments on Mir space station and earlier Soviet spacecraft like Salyut mission back in 60s and up to 2000 where Mir was brought down. I think they have traveled more, but we are on stop anyway. One of very important success stories of S-Cube definitely is the imaging capability, and up to at this point, as you heard yesterday from Andres Slavinskis, unfortunately Henrik Uuste, the father of our camera, is sick at home and can't participate, but we have great results in that respect. But I go into detail a little bit later, but this is something that gives us excellent opportunities for different novel aspects of science popularization. Because just a couple of days ago, at the birthday party, I was sitting next to a geography teacher. And then we started to discuss what kind of active learning materials for primary school and high school could be developed based on images taken by SQ1, and we figured out that that would cover like half of primary school geography related to continents, atmospheric things, and for example, rivers carrying some mud into oceans, and you can see all of that on SQ1 images. And then we thought that we really do it. We are going to do it next year. So we put together a collection of, handbook, what's it called, Töövihik. So workbook for schools based on SQ1 mission. Also part of this outreach is the next number. Since the launch of S-Cube, I counted it's about 70 public presentations that we have given for Estonian or international community. International means mainly scientific conferences, but we also have had keynote presentations in very rare conferences. Actually, like just in beginning of July, I was in Riga. In Riga, Latvians organized a very big international conference on organizational values. So it's International Association of Researchers in Organizational Values. And they were very interested what kind of values have kept this very strange team of more than 100 students and engineers and professionals together over 5 years to develop the satellite. So at least I could get them entertained, if not into believing that students can do really great science, even at undergraduate level. But yeah, I didn't have any students with me, but students here, like Henrik yesterday, definitely can prove that concept. Andres, you want to say something?
I want to point out Henrik.
Yes. Thank you, Andres. And I would like to point out Andres, but I will point out him later when we talk about attitude determination. Some weird numbers. Yes, we have presented a number of publications, scientific publications to people. But one thing that in Estonia at least is very much used to evaluate the quality of science is just the number of articles that you find in the Web of Science. And SQ1 keyword brings you 7 papers in Web of Science at this point, and in Scopus, the second most important reference database, it gives 14 searches. Also, it's very interesting to note that Tartu University, it was announced just yesterday or day before yesterday, got a record high position in world university ranking. The record high means, was it 379 or something? But at least already a couple of years we are in this US database list, and last year before, we used to be at 470 something, 450, so almost 100 position rise which is really, really good because there are hundreds of thousands of universities in the world. So, and then our team member Mihkel Pajusalu gave very brief comment to that, because the method, if you look at how universities are evaluated, it's actually a popularity list. So like 40,000 professionals, academics are questioned around the globe to find out which universities do they know. So, and comment from Mihkel Pajusalu, our EPS chief, was that, at some point after STube1 launch, Google search gave more returns to STube than it gave to Tartu University. So, guys, you could be proud of your results. I'm pretty sure that Tallinn Technical University has benefited equally from STube1, because we have never spoken about STube1 without mentioning the other Estonian universities and our international partners who have contributed to this mission, like Tallinn Technical University, Estonian University of Life Sciences, Estonian Aviation Academy, and, and long list of international partners like Finnish Meteorological Institute, Aalto University, Helsinki University, University of Jyväskylä, University of Eastern Finland, and German Space Agency TLR. Now, 9 close approach notifications are also important, because this is something that some satellite groups leave unnoticed. Because you know how this works. US Air Force Space Command sends you email saying that in 2 days there is a space debris part will hit your satellite with probability of something. It will be at, let's say, 500 meters or 200 meters distance from you, without certainty of much more. So, as Jens Taskard Nielsen from Aalborg University, who will speak to you tomorrow, he said that for AAUSat, they got so many of them, they don't pay any attention. But we definitely have managed to take advantage of these notifications by making the first of them public in Estonia. And we've made the front pages of Estonian biggest daily newspapers with the news that our dear little satellite is threatened, is having a big fight with evil space debris in space. And using the right words like this nice, cute satellite, not cube satellite, but cute satellite, is threatened by evil space debris, definitely caught the attention of people, and I think this the fact that people really got intrigued and influenced by this news is definitely saying that they were already ready to recognize the satellite as one of us in space. And to desert deployment tests is one of the most important numbers from the scientific point of view, and everybody active in science already knows that if it's not 1, that's already maybe a little bit bad sign, but I will get to that now shortly. From engineering science point of view, here is a more detailed list of our science behind STube. That means all subsystems, most of the subsystems on STube1 have been original designs by our students, and that is one reason why STube development took so long, 5 years, but it's also one of the most important decisions, I would say, the best decisions that we took in 2008 when we started our program, because that has really gave a lot of educational impact. Most of the educational impact from our project has come through this development. And starting from electrical power system, then it has been a nice source of new information that we could have shared with our colleagues through different presentations at conferences and journals. And maybe just in 2 sentences, I ask our team member, EPS team member, Erik Ilvis, to say the most important lessons learned from electrical power system design. Erik, please.
So our EPS has performed better than expected, but as you can see on the corner there, there's the drop in solar production, and most likely it's due to the contamination of materials outgassing. So outgassing is definitely one thing to consider when
Thank you, Erik. And this gives a big hand to our ETS team. Structure and communication. It seems like a simple thing to keep the satellite together, but actually it's turned out to be a very complicated thing. When we took the satellite to the first vibration tests, and our team member from Tallinn Technical University and the company PL Space, Paulias, has been in lead of this development for years, and one of the first important success from orbit, deployment of the antennas, definitely was one of the great achievements of Paulias. And Paul, would you like to say 2 sentences about lessons learned from S-tube structure?
Yeah, it's easy. Just keep the whole system simple and prototype as much as you can. And I think that we'll hear more about it later today. So keep prepared.
Okay, thank you very much, Paul. And communication team is not here today, but great thanks to Tallinn Technical University and company Defendec, where our engineers, at least one of them works now, and I can only say that works as it should. So they are doing a great job. Our imaging system works also excellently, as Andris introduced yesterday, and I won't add much to that because most of you heard already. But if we list the greatest successes, is that European Space Agency's ESEO mission welcomes us on board with our payload, and this is definitely because of the excellent work of Henrik Uuste and the others on imaging system. Our command and data handling system just briefly works as supposed. Maybe our command and data handling system lead Indrek would like to say 2 sentences about the most important technical lessons learned.
Yeah, well, I don't know what to say, but actually on S-tube 1 we sort of under-designed command and data handling a bit so that it wouldn't consume too much power. But on the other hand, this made it difficult to implement attitude determination algorithms on board. So on the next satellites, we plan to invest more on the onboard computational capabilities in order to make it simpler to implement those complex algorithms. And that's about it.
Thank you, Indrek, and CDHS team. Attitude determination was presented yesterday, and attitude determination, I think we can consider full success of the mission because, as Andris presented yesterday, we have achieved about 1.5 degrees uncertainty and performance of the attitude determination, not in eclipse, as was clarified by a question yesterday, but under illuminated conditions. And there is a lot of interesting publications. Andris presented already lessons learned yesterday. Attitude control is the next step, and as we presented in May, the Estonian public, then we had major problem related to unwanted magnetic field of the satellite, and this is a good moment to repeat what was said yesterday by Henrik, that attitude control has now completely solved the issue, and S-tube 1 spin-up works as needed for desert deployment, not exactly in the axis that was originally planned, but it works very well to fully satisfy the requirements for the desert deployment and the ESA test mission. So Henrik already said what we learned from that process yesterday. Now, as a desert deployment test, the most important test that the TSTube carries out in space started last week, and the procedure of the desert deployment is such that first we needed to burn logs for the desert reel and the desert end mass, and we did it. Our feedback system for success of this process comes from the power consumption monitoring, and we commence drilling of the tether. Also, we monitor it by power consumption and try to get the indication of success of the reading from gyros readings. And we took some images of the situation outside the satellite, and at this point I'm not so happy to tell you that we don't have any confirmation of successful tether deployment at this point. So, Johan Kütt, chief operator or chief of the experiment, who has committed a lot of brain power into conducting the test, and who was behind solving the magnetic field issues, would you like to give a couple of sentences comment on the next steps of the tether deployment testing?
Right. As Martin said, we at the moment have no confirmation that the tether has been deployed. There are several different options. The tether may have been broken, and then may have already flown away from the satellite. There is an option that the reel has got stuck, so we are getting some vibration and some feedback from it via gyros and the power consumption, but there is actually no way of telling if in fact it turned or not. So it's stuck on the tether and then are still in there. So right now our next plans are to, right now the satellite is spinning still at high rates, roughly 240, 250 degrees per second. So the next plans are to slow the satellite down so that the centrifugal force, if the NMAS is still there, the centrifugal force would reduce and maybe loosen something up inside the satellite. And then we will also try to spin up the satellite in the opposite direction just to do something different. We'll also try to burn the logs again at low speeds. And then we have a couple of, let's say, more hypothetical ideas for the coming weeks if those options don't work. So right now it's sort of spin down, spin up in the opposite direction, increase the spin speed. Just basically try to change the forces acting on the satellite. So, and if anyone has great ideas, let us know. So we're sort of in a few weeks we'll be starting to run out of ideas.
Thank you, Johan. And we can give him applause for definitely solving the control issues of the satellite, which I would say is definitely was one of the greatest learning experience, because from educational point of view, the more trouble we have, the better it is for the students, because they can solve them. Now, what's ahead of us? When we don't know how will we succeed with the tether deployment, but we know that ST1 has achieved many important scientific objectives and engineering science objectives. And for example, the attitude control and spin up of the satellite to 360 degrees per second rate, or in coming week maybe up to 400 or more degrees per second with magnetic coils. This is something that nobody has managed to achieve before on CubeSats. So that definitely is a breakthrough for our technology. And we definitely continue to characterize this attitude control system in order to have a proper report for the colleagues to learn from. We also definitely continue testing our imaging systems with different functionalities to have also complete report of the performance. We definitely will test electron gun that has been developed by Jyväskylä University using MEMS technology for our mission, which is also very interesting. And we definitely continue monitoring the long-term performance of all our subsystems, which also will give important information for all CubeSat community. And at this point, I would like to thank all team and all people in the hall, and I hope that you will also benefit from the experience of our student team when you develop your machines. Thank you very much.
Thank you, Mart, for this wonderful, I would not say presentation, more like a show, but maybe there is some questions left. So I guess that then we will continue to the next presentation, and I forgot the name of the town. Laurinas Masiulis, please, from Vilnius University. And now we have, I guess, more or less first opportunity here in Estonia, in this hall, to hear how the Lithuanian satellite is performing. And I really hope that in the future we have more Baltic satellites to present here. So.
So, at last. Hello everybody, it's a pleasure to be here, and I'm very excited because this is our first international presentation of Lithuania's at one, and I'm really happy that it happened to be here in Estonia, because these missions, of course, are very important for our Baltic countries. Because we share the same dreams. We share the same dream to go to space independently, and I'm really happy to share our success story here. So, my name is Laurinas, and I'm right now associated with Vilnius University. Let's start the presentation, and the contents is right here. You see, I will start from the background story, then run into project management issues that we faced, and present the system design, mission operations, and lessons learned, and then in the end, until the future project goes. So, most of you probably don't know that actually the idea of the first opinion satellite in terms of our Lithuania Sat-1 project, they happened to be started not in Lithuania, but on the other side of the world, actually, in the USA. And it's really, I think that often the case is that you share the ideas and you find people that inspire you to do very ambitious projects. So that was the case with me and my colleague Dennis. So we had a chance to go for internship at NASA Research Center. And over there, we answered that finally the question, what do you need to do to start building a real satellite? That was really our dream. And the answer was just to drink a cup of coffee with the right guys in the right place. So I think that's really where you start from. You really find really inspirational, talented people who motivate you to start doing this. And as Jan told yesterday about the systems engineering and all the procedures you have to follow in the engineering point of view, I think what is also important is the ingredients you have to put to have a successful mission. And we found that our ingredients are, first, is to work hard. And I think everybody who, if you talk to anybody who launched CubeSat, they will confirm that you have to prepare to work hard, to work at nights, to work on weekends, and that's the reality of this. You have to give yourself fully to that. Then the other ingredient that we found important is the team building. No matter how smart you are, you still need a team to accomplish your task, because the joy of sharing your idea is much more rewarding than just doing it yourself. And then the last but not least is you have to have passion in what you are doing. And in our case, that was really, I could say, most important ingredient, because we faced a lot of difficulties during the project, and the only thing that kept us going was really the passion that we liked what we were doing. And of course, don't forget the coffee break. So those of you who were not here yesterday, some students did the mission idea preparation. So we found it much more enjoyable to do that during coffee breaks. So we used to take napkins while drinking coffee with our supervisor at NASA, and we just tried to draw sketches and write mission objectives and just move forward. So we crystallized our mission statement, and the first one was that we clearly understood is that we want to launch the first Lithuanian satellite, and that has to be a 1-unit CubeSat size. And the reason for that I will explain later. Then, of course, we wanted to connect the industry and academic world so that an interdisciplinary interaction would help develop this infrastructure in Lithuania that was not there at the moment. There was no space industry, there was no so much space interest in general in Lithuania. And then the third point was that at that time, it was the coming anniversary of the 80th anniversary of the flight across the Atlantic by Lithuanian pilots, legendary pilots who are sort of national heroes in Lithuania, so we thought that is a very good association to dedicate our mission. So that was our selling point, so to say. Then, after that happened, the internship at 2012, summer of 2012. And then, of course, when we came back to Lithuania, the harsh reality faced us how we implement this. And so, the unique thing about our project is that we didn't have a national program or a university so to say, establishment that was running the CubeSat project, we started ourselves as a private citizens. So we founded a non-commercial company called Innovative Engineering Projects, and two of us started to accomplish this project. So the way how it worked is that we contacted Nanorex, a private company who has a space act agreement with NASA to launch commercial vehicles to ISS. That happened during our internship, and they really helped us to find a way how to launch the CubeSat. So we had a launcher, basically. The Nanorex then did all the paperwork and all the legal communication with NASA. We didn't have to deal with NASA at all. So then, of course, we knew that we want this project to be educational from the very beginning, and we were looking for students and scientists who would like our idea, and that really happened naturally. Couple of guys came from Vilnius University. We introduced the idea, they liked it, they started building it during their leisure time, and maybe after half a year, the whole university was just, so to say, persuaded to support this project officially. And that's how we actually got a very good partner, Vilnius University, who also raised the funds to pay for the launch costs. Then, of course, there is our second mission objective, as you remember, is to connect industry. So we thought how we shall raise the cost to build a satellite. So the way we did this, that we went through the companies and said, hey, we are building the satellite, maybe you can help us. So some of them build the solar panels, some of them build the structure and other components, and that's how we assembled a huge team. And not only industrial companies, but also the media companies and also the private, some of the private citizens also were beneficiaries and also donated some money for us. So that's how we built the satellite. That was our project management model. Of course, that was very challenging, and I will tell you what were the lessons learned from that. Of course, mission objectives, not to forget the system engineering approach. So the primary mission objective was, as I said, to build and launch the first Lithuanian one-use-size CubeSat. And then came the important thing, is that not just launching the satellite, but we thought it would be great to have a first message coming from space from our CubeSat. And that was actually the way how we thought we can attract attention, public attention, and maybe have a better selling point for the private companies to fund it. Then the secondary mission objectives were the educational. Then we wanted to develop our own onboard control and in-handling subsystem to use in future CubeSats. We wanted to take pictures. We didn't have, actually, that's a bad system engineering approach. We didn't have very precise requirements, but that was more, I would say, a philosophical way of thinking, is that usually you associate a picture of Earth and space as a kind of a symbolic achievement in the history. So we thought it's very important for the first mission. I think that was the same for the SQ. And then we had also an objective to test an amateur radio FM transponder that was built by our radio amateurs. So, success criteria. First, of course, just minimum success. We need to launch it and we need to know that it works. Of course, then we want to establish two-way communication, turn on the FM voice repeater, and the important stuff in the FM voice repeater was actually the voice message that I will tell you later. And of course, the most challenging task as we saw it was taking a picture and downloading them. So our schedule approach, first baseline was very optimistic. This was laid out during our internship. Our goal was to achieve everything in 1 year. That proved to be impossible for our project, but we still think we could have done it if we had reliable funding. But as you see, we shooted for the HTV4 launch from ISS that happened actually a bit later, and I think that was happening in July 2013. But we had a plan B to launch with SpaceX. But SpaceX was later delayed and we were switched to Orbital 1. So then 1 year later we had a little bit different schedule. So we still struggled with software integration and with funding. Since about 30% of our components were commercial off the shelf, we needed to buy them, and we didn't have initially sufficient funds to procure all the hardware. That's why we had to delay the project. And in the end, it happened so that our integration phase got so compressed that we really faced a lack of time for all the testing activities. So actually, you see the CDR happened in August, and then basically 2 months later we launched the satellite. So it's not really the way you should do it. But that was our only choice at that time. We didn't have any other scenario. So I don't want to make this presentation too much technical. I think I will run through the subsystems, how we designed it. So electrical power system. We thought that from the very beginning we don't need to design our own EPS. We bought the commercial one from the GomSpace. So it is expensive, but we found that it was really reliable. So you have to pay the price, but also the other factor was that the batteries that were used there were space proven, and when you want to launch from ISS, a very big pain you have is the battery issues, and NASA is very, very careful with that because you don't want to explode in ISS. So this eased a bit our situation because GomSpace had other customer who was launching for ISS, so we still had to do all this certification stuff for it to work. So we were on the safe side, although we still have to provide individual tests for nanorites. And then the other interesting point is that ISS safety requires to have 3 switch-on inhibits on the CubeSats, while generally you have 2 with other launchers. And what they wanted to do is that we have mechanical inhibition, because on the GomSpace general design, the initial design was this MOSFET switches that really were just the switches, and they were not mechanically cutting the circuit, so we had to have the extra switches that we placed on the side of the rail that actually cut the ground terminal of the battery. but happily, just before we bought the EPS, we did a revision according to ISS safety requirements. So we didn't have to cut traces on as others had to do. Our solar arrays were in-house built. We plan to put some more efficient gallium arsenide cells on the sites, but unfortunately we didn't have enough funds to buy them. So we designed the power budget so that it would be feasible still with the silicon to support all the power requirements. And also the advantage of the silicon was that the factory that produced them could cut the individual cells to the form factor that we required so that we can use as much area as we can, as you see from these drawings. ADCS approach was very simple. Passive magnetic additive control with permanent magnets on the longitudinal axis and hysteresis rods on the cross-sectional plane to dampen the oscillations. The onboard computer was redundant in terms that we had two controllers. One of them, the based on ARM, was carrying out the main functionality, like power management and communications to the ground, scheduling, task management. But we still had a secondary computer that was based on Arduino, and that was one of our ideas, is that we wanted to prove that it's feasible to run Arduinos in space, to really improve that. So the Arduino was responsible for taking pictures and controlling the radio beam. So the communications hardware, we used commercial off-the-shelf components like the helium transceiver from USA, running in GFSK, and a small FM beacon that had, by the way, the space heritage, and it's already, I think, more than 4 years in orbit on the Turkish satellite. The lesson learned was, probably will forget to mention that later, is that we think that it's too much powerful and the power consumption is too high for such a device. And we don't think it's really critical for the mission success, although we thought that during the initial phase, when the CubeSat will fly very close nearby, it will be easy to use the FM to distinguish whether our satellite is working and to do the troubleshooting. So we faced some challenges with antennas. We completely rejected the option of commutation for the communication link. So since we had transceiver, FM beacon, and FM transponder, we had 3 transmitters and 2 receivers. So the way how we did it, we did separate transmit antennas for all the transmitter, and the VHF antenna that is a bit longer was shared by 2 of the receivers because we didn't need them at the same time. So also the consequences was that it was, as our supervisor called it, appeared like a Christmas tree with all the wires coming out. So, and we wanted to wrap them around to use this classic fishing wire approach. That was the most simple approach, I would say, but it has some technical challenges. And ISS required us to design so that in case of inadvertent deployment of antennas inside the deployer, the satellite could still be pushed out and will not stuck in the deployer, so that the cosmonauts will not have to go out to space and fix it. So the way how we did it is that the antennas are all connected to the minus Z side of the CubeSat, and they deploy in the direction of the pushing of the satellite. So it would still, the pace of the deployer will not cause them to stop. The structure was sheet aluminum. It was a mixture of pumpkin and our own design features that we now think was a bad approach. We think that a sheet metal structure has some drawbacks in terms of integration. For example, if you have, I will show you in the next slide what actually was the problem. So it's sheet metal structure, and here you can see all the subsystems, how they were fixed to the avionics stack. So payload, the camera was really simple one. We didn't invest time to create our own. Of course, maybe the pictures are not so beautiful as this view, but it still worked. And we just put our own optics on the camera, and we designed our own aluminum frame instead of plastic frame. So we just redesigned the commercial off-the-shelf camera. We put wide-angle optics to increase the field of view. And the good thing about this was that all the processing was done on board. We didn't have to care about it. But the disadvantage was that we could not control some parameters of the camera, like the shutter speed and white balance, and of course we forget about the neutral density filter and infrared cutoff filter. So the FM transponder was really, I would say, our most important payload, because it was really built in Lithuania from scratch. That was the main technology demonstration that we wanted to show, and the idea was that we wanted to prove that you can operate simple FM transponder in a CubeSat, and you can communicate it through it using simple 3-diameter equipment. That was our main task. And if some of them have any questions regarding technical, I would be happy to discuss later, and I can give you contacts of the guy who created it if you want more information. This is just general layout. We had 5 boards: motherboard, receiver, and EPS, onboard computer, and the transponder. 3 switches, as I said. Then the challenge with the integration was, as Jan said, the good thing to remember is when you do prototypes and you design in CAD, don't forget to put the female and male connectors in your model, because we designed in the CAD, it seems that like it fits, but when we tried to put all the cables, it appeared that it doesn't fit to the structure. So we had our solution was to actually solder out the connectors and to solder the wires directly to the RF output. But we don't think this is a good approach, although it worked for us. And also, when you imagine this stack that you have to put in the sheet metal frame, then you obviously imagine that when you put everything inside, you don't see what happens. You have some obstructions, and it was quite difficult to put everything so that it fits very easily. And if you forget something, then you have to take everything out again. So that's the drawback of this structure approach. So we would recommend to use framed aluminum like one is. So mission operations. We launched from USA with Orbital 1, the first orbital resupply mission in January. Then we had to wait for deployment that happened more than a month later. Those of you who didn't know, there were actually 2 Lithuanian satellites launched at the same time. And you see, here is the LitSat-1 from Vilnius University of Technology, and this is the LitSat-1. So, 2 Lithuanian satellites launched at the same time in the history of Lithuania. So I think this is a great achievement. The first signals appear to be very weak, but of course we expected that because the first pass was very low and the satellite was spinning and tumbling. But the telemetry proved to be nominal. The battery voltage was 8.3 volts, 100% capacity. The power generation was 210 milliamperes. Current draw was 112. Temperature was a bit lower than we expected, although it is logical, but because the satellite was in the before turned off, so it cooled down a bit sometime. So everything seemed normal, but then we noticed a bad thing, and that was this curve. And this shows the battery voltage during the first 4 days of the mission. And as you see, it gradually went down, 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 down until it reached some software set safety level in the EPS and the satellite went silent. Of course, that was bad news for us, but we tried to do analysis what went wrong, and really it didn't took us too much time to find the root cause, and that was actually the abnormally low photocurrent from the solar panels. The strange thing is that the solar panel voltages appear to be nominal, but the current was not. And we still have not identified what is the real cause of that. We suspect that it might be the bad PowerPoint tracking settings in the EPS, or it might be some hardware failure. So the good news was that the EPS has an under voltage protection system, so it's a good feature you should have in your satellite. You set the limits, and the way how it worked for us is that it prevented critical failure, mission failure, but it did not solve the problem, because it turned to be that the FM repeater actually draws about 50% current in safe mode. So the bad thing was that the power budget was still negative in this mode, and when it reached this mode, we could not actually control the satellite, because in critical mode we turned off all the subsystems. And we had to wait so it reaches safe mode, and then back normal, and the satellite, sometimes in the past it was active, sometimes it's not, so it was difficult to get in contact with the satellite. So the solution was turn off the FM beacon, but it proved to be not so simple as it sounds, as I said, and one of the reasons for that was that the uplink budget was too low than expected. We think that's because of the antenna pattern and deformation in the steel antennas, while it was still wrapped up around the structure. So we needed at least 100 watts of output power, so we put the amplifier, and it proved to work. And as you see also from this slide, from this picture, this is actually the sequence of photo, the photo download, and you see that the signal is fluctuating, and this was due to the spin along the stabilized axis that was uncontrolled. It was about 2 revolutions per minute. And since we had some dropouts in our antenna pattern, it happened so that at some time the signal was good, and then when the pattern got in the direction the dropout was the fade, and it really was, we noticed that it was both for uplink and downlink. First very good success was that we finally managed to get the power problems solved. And the first thing that we done was we turn on the fan transponder, and the first message was actually the salutation of the Lithuanian president. And the story behind that is that once we had the presentation of the CubeSat in our university and the president came, we had the satellite turned on, put the two radios, and gave one to the president, and she just said some nice words, and we thought that should be our voice position in the satellite. So that was really not planned. And then, of course, we operated the transponder. It was really successful and really surpassed our expectation. The signal was very strong. This is a nice picture from Mike Ruprecht, where it shows how the frequency changes due to the Doppler, and also the signal strength was the communication activity all during the past. So we got really good feedback from radio amateurs all around the world, especially, of course, many of them in Europe, but also many in USA, and we actually got the Oscar designation number about 1 month before our mission end. But that's really very nice to have. So the first picture we had was not really impressive, as you might say, but still, as the president said, it's kind of as a work of art. One of our friends likes to joke that we proved that the Earth is flat. That was due to some spherical aberration of the wide-angle optics. And at least what we were happy is that our antennas actually deployed. So that was the good news. And then, of course, we had nice pictures of the Earth that took some time actually to acquire, because since we didn't have active control of the attitude, we had really to plan and to try all the combinations when actually the satellite is looking to the Earth, because it appeared that it's a bit oscillating about magnetic field, and we really didn't expect such an image, like facing almost directly to the nadir direction. This is actually the photo of some Mongolian steppes with the lakes. So I would like to go to the close of my presentation, because you are all very hungry. So lessons learned. We found that when you are running the project as a project manager, you need to understand the stakeholder expectations, because when we had a lot of stakeholders who had different expectations, they had different interests, and it proved to be difficult to join everything into one. And some of the stakeholders had to actually leave our project because of that. So also be prepared for budget overruns, as always. Then we would strongly suggest to avoid protoflight philosophy. Protoflight means that you build the satellite, you test it, and you launch the same satellite, instead of having one dedicated satellite for testing and development and the other for flight. Because that's very risky. If something goes wrong, you are in a big trouble, and I'm really happy that we didn't have any problems, because otherwise we would probably fail our project. And the other important thing is that when you don't have extra model, you cannot do troubleshooting after you ship your satellite. And that's really bad thing, because if you had the same identical satellite, we should do some troubleshooting to know the reasons of the failures. Software integration took more time than we expected, and probably will have happy to do, so be prepared for that. Always test as much as you can. You can usually avoid most of the problems while testing on ground, not have surprises in order. And keep your documentation up to date, and of course don't forget to use it, because some of our guys did some stupid adjustments in the satellite that we only knew after the launch. And we really suggest you have a guy dedicated to keep track of everything what is changed and done in the satellite, because engineers usually don't like to write stuff and to read documents. So, instead of conclusion, I would like to introduce our next project. It's Lithuania Sat-2. We're going to plan to fly in the QB50. So this time we have a scientific justification to do the exploration of the thermosphere using the QB50 scientific unit. And also we have a technological case where we want to demonstrate the green propulsion system that is shown here with the approximately delta V budget of 150 meters per second. So we are flight accepted at last, and we are almost done and ready to build the satellite. So thank you again, Mark, for inviting us, and it was a pleasure to share our experience, and I'm happy to answer any of your questions.
I'm really proud that we can welcome the first Lithuanian satellite here in Estonia, so it was really great, and I'm happy about your success. So, question now. Yes.
So what kind of special battery testing was required for ISS?
Well, they wanted to do a vacuum test and vibration testing, and what they wanted is that we measure the dimensions of the battery and see after the vacuum and vibration it doesn't expand, and we wanted to do all the open circuit voltage measurement and all other measurements to do if they don't change, so that there's no chemical things going on in the battery that would be dangerous. That's all that we want.
Yes.
I have a question about this power system and feedback you mentioned. How much have you tested before launch with that? Or did you have very short time? But also, how much have you talked to GomSpace afterwards? And what was their review on this?
On the power problem?
Yeah, normally low power problem. Because it tracks back to their system in principle, right?
Yeah, so the really disappointing thing that we didn't have time to test it. That's why we didn't notice it on the ground. We did the functional test. We saw that the PPS, the solar cells are charging the battery, but we didn't measure the performance. What is the current of the charge? We just checked that it's charging. We thought, okay, it works, but that proved to be a bad idea. And we communicated with GomSpace, but since they are a commercial company, since we didn't buy their own solar cells, they thought that was our problem. They don't really take much consideration with that. Although they helped us with some specific questions on EPS.
You don't think it's an intrinsic problem of the power system, it's rather the settings which were not investigated?
We suspect that, it might be the power point tracking that was not really designed for silicon, maybe. And as soon as we have a chance to rebuild the satellite again, we think we will find the renewables.
I have another very short question. You mentioned there were 2 satellites launched.
Exactly.
So
you have
how did it go for the other satellite?
You will have a presentation of the other team, Mr. Rigmandes will introduce the second project.
Thank you, and I guess that we need to leave the further discussion for the lunchtime. You will need to stay in the queue anyway, so you can discuss. And thank you very much again.
Thank you.